Hello, Physics 20s. I want to actually go through the notes on gravitational field strength and just the force of gravity. And I'll add a couple of things and give you some tips as you're trying to work through some of these practice questions. So, sorry, I was just looking at this. Let's go back to the top. So these are the introductory notes to gravity. Gravity is one of the four fundamental forces that governs the universe. Um, in Physics 20, we only talk about gravity out of the four. You take Physics 30 and we'll study the electromagnetic, the strong and weak nuclear forces. They're all really fascinating. But essentially, those are the forces that govern the universe. Um, Newton classically studied gravity. In fact, up to his day, no one had really been able to explain why, the moon orbits the Earth, for example, or why the planets orbit the sun, because no one really understood gravity. Newton proposed that and actually came up with a formula for that. So that's what we're going to look at today. Gravity is the weakest force, but it acts over the greatest distances. And we'll talk about that later. Forces that act at a distance, they called those action at or action at a distance, because these forces, you don't have to have two objects touching each other for you to be able to experience a force. You can feel it at a distance. So Newton developed what became known as the law of universal gravitation, and it's based on these two things. The force due to gravity is proportional to that. I'll maybe just write that off to the side. It's actually the Greek letter alpha, um, which means varies as or is proportional to. And sometimes you'll see that in some of the questions if you ever see this little symbol right there. So this just means the force of gravity is directly proportional to the product of the two masses, m1 and m2. You'll see when I write the formulas, I actually do a capital M1 and then a lowercase m2. And I do that on purpose because M1, the big one, is typically considered the big mass or the larger of the two masses. But sometimes we call it the source mass, but that doesn't really matter too much because mathematically it's the product of both of those. Now, Newton also came up in his observations with another expression, and that is that the force of gravity is proportional to 1 over r squared. R is the separation distance. Okay. And that's from center of mass to center of mass. Sorry. Center of mass to center of mass. And it is r. I know a lot of times it actually is a radius, but just be careful in your mind that you don't always assume it's just the radius of a planet or something, because it's really from the center of one mass to the center of the other. And we'll emphasize that as we move forward. So just to show you what that really looks like, these two graphs here, let's look at this first one. This one shows the magnitude of the force on the y-axis and the distance from the Earth's center as just r, okay, or 1 Earth radii. So here you can see we're at 1 Earth radii. So we're on the surface of the Earth, and at that distance, we'll say that the force of gravity is 10 newtons. Okay. Now, if we were to move twice as far away from the Earth now, so now we're out here, look what happened to the force. It actually dropped down to, it looks like it's about 2.5. So what happened here is the force dropped by a factor of 1 over 4. And why that happened is because you look at the expression, it's 1 over r squared. And this is what students first learn in terms of understanding these proportionalities. If r was doubled, which we just did it, right? We doubled the radius here. Whatever you do to the radius, it gets squared. I know my marks there are a little big, but whatever you do to the radius, it gets squared. So if you double the radius, it actually winds up becoming 1 over 4r squared. Okay? Because 2r times 2r, I guess, is 4r squared. So you're really changing it by a factor of 1 over 4. Okay? And that pattern just keeps repeating itself. If we go 3 times as far, that's 1 over 3r squared, like that. So that becomes 1 over 9. Okay, 1/9. So if you triple the separation distance between two masses, the force of gravity drops by a factor of 1 over 9. And in your mind, that might make sense anyway, like that if two masses get farther apart, that the force of gravity acting on them should get weaker and weaker, and it does, okay? And just in the reverse, as you get closer to something, two masses get closer together, the force of gravity should increase between the two. So this other one shows it as well. Just quick, you can see that this mass that's sitting out here on the surface of the Earth, it experiences a force of gravity of some amount. But if you didn't change anything other than you doubled the distance, so now you're 2r away, now the force of gravity is, sorry, I blocked that there, it's 1/4 the force of gravity if you double the distance. And then if you triple the distance, here she is way out there, right? 3r, you triple that distance from center of mass to center of mass. That's what r actually is. And you'll see me, whoa, I kind of had fun there. You'll see me sketching that or recognizing that r is the distance between the center of mass of in this case, the Earth, to the mass of like the satellite. We're going to be learning about satellites really quick here. So the formula that you need to know is the formula that Isaac Newton proposed was the expression or the relationship for the force of gravity. And this is it here. The force of gravity, Fg, is equal to big G. Now, let me just slide this over because you have this on your formula sheet. Big G is the universal gravitational constant. It's this number. Now, this number actually Isaac Newton wasn't able to determine on his own, as best as I know. It kind of evaded him in terms of accurately being able to find it, and it wasn't until years after his death that a man named Henry Cavendish figured out this number, but we'll cover him in just a second. So, but that's what big G is. And then you use that number every time, 6.67 times 10 to the negative 11, and then it's multiplied by the product of the two masses, m1 and m2, and then divided by the separation distance in meters squared. So you'll get some practice with that. It's not a horrible formula, but you do need to go slow and make sure you get your powers of 10 correct. And if you remember, I showed you that trick using your calculator where you use the second function EE button on your TI-83s. I'd really encourage you to use that. We're going to be dealing with monster numbers now in terms of masses of planets and separation distances. And if you use that, you'll be able to kind of cleanly do these calculations on your calculator. How did Henry Cavendish figure out the universal gravitational constant? He used a very intuitive device called a torsion balance. And this is a picture of it here. I guess he famously had one built, and I don't know if he pumped all the air out of it or not, or at least he eliminated, the wind or air currents or anything like that. But how this device worked was he had two masses that were suspended kind of like on a dumbbell, okay? So like these two masses here, and this doesn't show it that great, but there were two other masses that were stationary, okay? And the stationary masses obviously didn't move, but kind of the dumbbell masses were suspended from a cable up at the top, and they were free to rotate. So what would happen is, this mass might be attracted this way, and this one might be attracted that way, and so the whole apparatus would spin just a little bit. And Cavendish figured out that he could measure the torque or the twisting force up here in the cable. He could measure the twisting force there, and that twisting force would be directly proportional to the force of gravity that was attracting the masses down below. Okay, and just doing a number, like doing lots and lots of very careful measurements, because remember, gravity is super weak. He was able to determine big G. Now, we do it today, and it's been confirmed like hundreds of times, I'm sure, using this, a very similar apparatus. We can get really precise with it. So if you look at this setup here, you can see the torsion fiber. That's actually, they stick a mirror on that, and then they attach the dumbbell. as I call it, or just a rod that has two free-floating masses in it. So if you bring in these masses here, at these two purple ones, are the stationary masses. They don't move. So if you bring them in, or if you lower the dumbbell masses, they will attract each other. Okay, so effectively, the small masses will rotate like this. So that means then that this torsion fiber is going to spin up here. It's going to twist a little bit. And it's not very much, but if you use a laser, as shown here, that laser can hit the mirror and then reflect off and make a mark, or at least show on a kind of a graduated display how many degrees of arc were, had, or how many degrees of arc the apparatus moved through. And those types of measurements enable us to determine the twisting force. So you should just be generally familiar with the torsion balance. There may be some questions that deal with that, but the force of gravity that exists between these two masses is calculated by Newton's law of gravitation. So you would come right back to this mass, right, or to this formula right here, and you would calculate the separation distance, and that's actually what Cavendish did. He figured out the separation distance by trying to look through little viewing points, like you can see him here looking through, and he'd have to kind of do some measurements. Anyway, it was super tedious, but he was kind of eccentric, actually. So many of these guys were in determining the gravitational constant. So the next part here emphasizes the difference between weight and mass. And what we need to separate with that is weight is always the force due to gravity on an object. So and we've been using that already. Force of gravity is equal to mass times g. Anytime you're asked to solve for weight, that's what you use. Mass is totally different, and mass never changes. Your mass is a measure of the amount of matter that makes you up, is how I like to say it. And it's measured in kilograms. As weight is not measured in kilograms, weight is measured in newtons, because it's a measure of the force of gravity. So I always smile in Alberta at our driver's licenses. It says your weight, and then it says in kilograms, and I'm like, mm-mm. So anyway, that's just a little kind of a social thing we just ignore, because using newtons is not very well understood, at least not in the general public. So we don't have your weight posted in newtons. That would be really cool if it was. But anyway, so these notes emphasize that you can determine the mass of an object using gravity. If you use a simple scale like this, if you have a known mass on the left and your unknown mass on the right, if you can get those to balance, then you can determine the mass of an object now using gravity. Okay, so effectively, you could take this scale to any planet. Okay, we could go to the moon and use this scale, and it would still work. The force of gravity would be less on all the masses, because little g, which is the acceleration due to gravity, or what we're going to learn shortly here, it's called the gravitational field strength. Little g on the moon is much less. It's like 1/6 of what it is here on Earth. But a scale like this would still work on the moon. In fact, it would work anywhere except for maybe deep space, or on the International Space Station, which there the perceived gravity is 0 because of the nature of how it's orbiting the Earth. But so you definitely need to know the difference between weight and mass. I did post a video on the tides, and you should understand that generally as well. Tides are really fascinating. The moon is the cause of the tides on the Earth, and it's a little complex in that the moon actually exerts the strongest force on the mass of water that is closest to the moon. And I'm kind of circled that here. This is obviously exaggerated, but the separation distance from like the center of the mass of the ocean right there and the moon is much shorter than the distance from the center of the Earth to the moon, okay, than that distance. And so the I'll maybe clear that off. So what happens is the moon exerts a stronger pull on the oceans on the right side of the Earth in this diagram. So they get pulled towards the moon. Now the Earth also gets pulled towards the moon, but not as much because the center of its mass is a little further away from the moon. And then what's really kind of not that intuitive unless you think about it is if the Earth is kind of getting yanked to the right, then this mass of water over here is kind of being left behind. It's almost like you're pulling, you're pulling the tablecloth out from underneath the dishes or whatever, and the dishes get left behind type thing. So this mass of water sloshes out at position B. So the tides happen actually twice a day because the moon in its orbit, it'll go around the Earth, obviously, and that's what that video shows. So when you're on this side, obviously, if you're over here, then the everything is reversed. So at any time, at any position, basically at the ocean, you should see basically two tides a day, a high and low tide each day from that. Now, the idea too is if there's alignment of large masses, then the tide can be even greater. And so anytime that the sun, and I'll maybe just sort of sketch that over here, and obviously this isn't proportional, but anytime the sun and the moon are lining up, okay, then the sun will also exert its gravitational pull on the Earth, and potentially you could see a greater tide when there are other bodies that are lined up. In fact, historically, I think there was, I think it was recorded in France, or something called the tide of the century, and that was when a number of the planets actually lined up. Now, I know that's sort of a Hercules reference here, but if all the planets actually were lined up in their orbits, then their gravitational like attractions would be maximized, and you could potentially see a stronger pull due to gravity because all the planets got lined up. So that is an actual phenomenon. Anyway, so and then I guess one other one here. This one's sort of cool. Interplanetary travel. In the past, NASA has used the gravitational attraction of the planets and even the moon to assist space vehicles or space probes in their missions. And Voyager 1, Voyager 2 is a cool story. They happened when I was 2 years old. They were launched, and they've basically been flying away from Earth for my entire lifetime, which is it's kind of crazy. But what they used was called gravity assist. And Voyager 1, if you can see its trajectory here, they shot it out such that it would, in its orbit, just come really close to Jupiter. And so if you kind of imagine here, it was getting pulled in close to Jupiter, and then but it wasn't going right at Jupiter, but it was kind of going just off to the side, so that Jupiter's gravity sort of pulled it in and then kind of slingshotted it. If you turn on some propulsion, or as soon as you pass Jupiter, then you can kind of get a little boost, and that's due to the gravitational attraction of Jupiter. Same thing happened at Saturn, and it kind of got another little push. And Voyager 1 is the furthest space probe away from Earth, any man-made object that's ever been launched from Earth. Technically, it's outside of our solar system now. As best I know, it is still operational, but it won't be much longer before its plutonium, I guess, reactor runs out of fuel, and then it can't charge its batteries, and then it's just a dead piece of metal floating out in interstellar space, which is pretty awesome. Anyway, so there are some applications in terms of the force of gravity. So I'm going to let you work on these questions on the gravitational forces assignment, these first few. Each one of these questions will deal with the gravity formula, the force of gravity formula that I just showed you. And maybe I will just make note on this one right here. Number 4, it talks about the force of gravity, or object A exerts a gravitational force on object B. So the force of gravity between them is obviously going to equal Gm. In this case, we could say MAMB if you really want, divided by R squared, the distance that separates the two. I call these questions proportionality questions because they teach you how to recognize the relationship between all the variables. So I'll maybe just switch colors here. The point is, the force of gravity actually is 5.9 times 10 to the negative 11. It's a very small amount. But it says, what would happen to the gravitational force if the separation distance is 4/3 of its original value, and then the mass of A is 3/2 and the mass of B is 1/2? So what that means is this 5.9 to the 11 is what we start with, but if we start changing the variables on the right-hand side of the equation, how does that change the amount on the left-hand side? So if we start with the separation distance is 4/3 its original value, what I would do is identify that the separation distance is being multiplied by 4/3. But what's really tricky, and students first learn this, is anytime you do something to the separation distance, you have to square it. So really this would be, basically it would be 16/9, okay? But I'll let you sort that out in terms of what's in the denominator. Now the numerator is a little easier because they're directly proportional. So the mass of A is 3/2, so you would kind of say, well, there's 3/2 in there. I would change that amount by 3/2, and the mass of B would be cut in half. So what we have to do is collectively determine the overall net change on the right-hand side. By what factor, we say, by what factor are you changing the right-hand side? And whatever that factor is, you have to change the left-hand side by that same factor, okay? So I'd highly recommend that you come up with a simplified fraction. Fractions, especially in the denominator, drive me crazy. I got to resolve them. So I'll let you work on that. But ultimately, whatever you do to the right-hand side of the equation, whatever amounts that whatever factors that you change it by, you then change the left-hand side. And that's the power of the equal sign. That equal sign is demanding that you do that. Anyway, so the last two questions deal with kind of a scenario I was posing before, where the Earth and the Moon and the Sun are all in alignment. And for these questions, if it says it says calculate the net force of the Sun and the Moon on the Earth. Okay, so and just a note here, you really should use your planetary data sheet that's on your formula sheet. I'd like you to use that. This one's got a little discrepancy. The separation distance between the Earth and the Sun is actually 1.49 times 10 to the 11th meters. Okay, not 1.5. They rounded up in this graphic or whatever. I think all the other numbers are good, but anyway, I'd like you to use your planetary data sheet. It has all the data you need, like the mass of everything and the separation distances from the Earth from the Sun to all the planets. And by the way, those are the distances from the center of mass to center of mass. You don't have to worry about the radius of the Earth yet. I'll show you that one in a minute. So the point is that what you do is you calculate the force of gravity between the Earth and, like, the mass of the Earth and the mass of the Moon over the separation distance between those squared, and then you do it again for the mass of the Earth and the mass of the Sun. Okay, so you're going to get two forces of gravity, and in this case, they're acting together. So if we just, again, we're saying what's acting on the Earth. So the Moon is pulling the Earth this way, and the Sun is pulling the Earth that way. So you have two forces of gravity that are acting on the Earth, and you just have to add them together to get the net force, okay? So the math's a little tedious, but not horrible. And then in the end, I just want you to see you just got to add them together because they're both working together. Once you get down to this one, though, I start throwing some angles at you because the distances haven't changed. The Moon is still the same distance away from the Earth, and the Sun is still the same distance away from the Earth. But now you will use the same math that you did in number 5, and you will now have a net force calculation. But what's a little, you have to remember this from when we studied forces. If the Earth and the Sun, the Moon and the Sun are acting on the Earth in this direction, then if you look at this sketch, basically you need to add those forces tip to tail. So you'd have, this is the first arrow I drew is the force of gravity from the sun, and then the second arrow is the force of gravity from the moon, meaning that you'll have a really slight angle now. Sorry, that's not a great angle. That the Earth's experiencing a force at. So you'll see that when I post the key a bit later, but I'd like you to try that. So you're still using, though, the universal gravitational constant, big G, and Newton's force, or his formula for the force of gravity. So I'm going to shift gears now and go to the next part, which is gravitational field strength. You can, once you get to that, you can pick up on this video. There's two methods to calculate gravitational force between two masses, and we've now covered both of those two right here. But there's another formula that we can derive from this, and it is actually the gravitational field, or the gravitational field strength. And it's a pretty easy derivation. This is actually what I was talking about earlier, this action at a distance force. So if you look at the Earth, the way that we can depict the gravitational field around the Earth is by using what we call field lines. We actually use field lines to describe the other forces as well, the electromagnetic force, magnetic forces, electric forces. We use what are called field lines. And they're a really simple drawing. Effectively, the field lines show the direction that a test mass, if we stuck a test mass, like a really small mass, near the Earth, if we stuck it right at that position, sometimes we call it position P. If you stuck it right there, what would it do? If you just put it there and let go of it, what would happen to it? Well, due to the attraction of the Earth, it would move towards the Earth. Now, actually, if you're catching this, the Earth would also feel a force of gravity towards this little test mass. But because the Earth is so massive, as you may have seen in that video, it has so much inertia, the amount of acceleration that it would experience towards this little small test mass is essentially nothing. So, but you have to remember that it doesn't, like, the size doesn't matter. The force of gravity is experienced by both masses. Okay, they both feel the same amount of force towards each other. Just that the one with less mass will experience a greater acceleration, and in this case, it will definitely move towards the Earth. So that's why all these arrows point towards the Earth, and you can see that the concentration of arrows gets tighter as you get closer to the Earth, which is supposed to represent the increasing strength of the gravitational field as you get closer to the Earth. So it's a fairly simple depiction, kind of like, you know, spokes on a bike tire pointing in at the axle, right? So if we want to determine the strength of the gravitational field at any point, then you measure the force of gravity at that point, okay? And mathematically, though, I know it's kind of written down below, but let me just show it to you right here in another way that might help you. What we can say is that the force of gravity is also the same as the force of gravity, but if we show this formula, which we've used a lot already, force of gravity on a mass is equal to mass times the acceleration due to gravity. Now if we combine that with the formula we've just been practicing, we can say that this idea of a test mass, okay, like this little test mass that we put in there, that mass is going to be the same as the second mass. Okay, I've been trying to emphasize that M1 is the bigger mass, which may help you kind of sort out masses. But again, mathematically, it won't matter. So that means, though, that M2 is on both sides of the equation, which means we can cancel them out. And that leaves us with another formula that you've not seen yet, and that is that gravitational field strength is also equal to this universal gravitational constant times the mass of the planet, or the source mass, the big mass, divided by the separation distance r squared. And that distance r is the distance from the center of M1 out to that point in space. So that way, when we're calculating the gravitational field strength, you don't need a second mass out at that position. You just need to know the distance away from the big mass, M1, and you can calculate what we're calling gravitational field strength. Now, what's worth noting here is that gravitational field strength is measured in newtons per kilogram. This universal gravitational constant has kind of some funky units. I didn't really emphasize that before, but it's kilograms meters squared. Is it kilogram meters squared per Newton squared? I think I got that backwards. No, it's not Newton squared. Where is she? There it is right there. It's Newton meters squared per kilogram squared. Got that backwards. Because basically the kilograms needs to 1 kilogram will cancel and the meters will all cancel. And you'll be left in the end with newtons per kilogram. So let's come back to that here, which is I was emphasizing that. So, but if you're catching that, newtons per kilogram is the same as meters per second squared. Woohoo. So when we use 9.81 meters per second squared, you can really say that that's 9.81 newtons per kilogram. So we can calculate the gravitational field strength if we just know the distance from the center of M1 out, okay? And that's what these questions here, actually not these questions, I'm going to come back to that. That's what these questions here are going to have you practice as well, is that you can use and actually for all of these questions here, you can use G is equal to GM1 over R squared. And so to finish up this video here, I may just quickly highlight question number 1 for you, and then I will let you do the rest of these as well, okay? And I'll come back to this middle section here because we need to emphasize some more definitions there. So in this case, this has an 80 kilogram astronaut and he's in an orbit above the surface of the Earth. So it says calculate the gravitational field strength at the location of this astronaut. So what you need to see here, which maybe isn't obvious, is we know the altitude, okay, above the surface of the Earth. Anytime you see that, that is not the separation distance. That's the distance from the surface of the Earth out, okay? So this is really 3.2 times 10 to the 7th meters, sorry. Because I'm converting kilometers into meters. Be careful that you do that every time because as you noted in the units, kilometers is not a unit we can use. So if we want to know the gravitational field strength, we're going to use this expression right here, above the surface of the Earth, we need to know the separation distance r. We already know the mass of the Earth. We can get that from the table right above or your planetary data table, which is on your formula sheet. But the kicker is this. You also need to add the radius of the Earth. Because that radius r, and I'm sorry I'm using r again, because that's the same as for separation distance. You need the entire distance for the separation distance, okay, r. So, sorry to confuse you with that. I should maybe just don't like that there. Let's just fix that. So you will need to take the 3.2 times 10 to the 7th meters and add to that the radius of the Earth, which is right there, 6.38 times 10 to the 6th meters. So doing that carefully will let you solve for G. So you have to use the mass of the Earth. It's 5.97 to the 24th kilograms. And you have to divide that by the sum of those numbers, which is actually going to be, I think it's 3.838. And you can check that times 10 to the 7th meters. Okay, but that number, of course, is squared. And so this becomes 0.270 newtons per kilogram. Okay, that's awfully small, especially compared to 9.81, which is what it would be if this guy was standing on the surface of the Earth. But he's way the heck out there. So out there, the gravitational field strength is much less. So I'm going to leave this video for now, and I'll post another one on the sheet above, and hopefully that's going to give you enough to work through this chapter, because these are all the concepts.